Okay, good morning. So let's continue the lesson. So we talked about integrals, and I motivated you that some kind of limit is important. I don't want to actually spend time again on it, but what we got is at least this interpretation is important for you to understand that if I have this is the x-axis and that is the y-axis, and then assume that you have a function y equals to f of x, it's continuous and it is above the x-axis, and then you have somewhere between a and b, you are interested in the area which is enclosed between these two vertical lines and this horizontal line and this curve. And if I call this area A, we realize that this area is equal to what we call an integral from A to B, your function f of x dx. Yes. So that is what we learned. And so far, if I tell you what is this symbol, you just tell me that this symbol means a limit of a sum of f of xi delta x, where I goes from 1 to n and n goes to infinity. Yes. And then if I tell you what is delta x is b minus a divided by n. And if I ask you what is xi, you would say xi is a point in the ith subinterval. Yes. After I start partitioning my interval into n equal pieces. And I also try to motivate you that sometimes in very few circumstances we can use this really crude definition to calculate this symbol. But that was not very efficient, and I told you that sometimes it is impossible. So, and then it means that now you realize that my motivating problem from geometry was finding an area below the curve. You realize that this area is this integral. This integral can be calculated using this, but is not efficient. We want to try to find another efficient way to calculate this integral. Yes? Okay, and I think this is good expressed in this book, so I will try to motivate you exactly what is written in the book. We want to understand the connection between derivative and integrals. Yes, we haven't done that, so you see that whatever I have written here, it's not related to the derivative at all. But now we want to understand the connection, the relation between the derivative and the concept of integral. And this is the way that I want to do it. For some reasons, I want to change the letter x, so I will keep this axis. I label it with t. I don't necessarily mean time. T is just another variable. And then this is the y-axis. Yes? And then what you see, I draw this curve again. Fy equals to f of x, no, f of t this time, because I have changed the label of x to t. I want to use x for another thing. I will fix one point here at point A, but I will let the second line goes back and forth. Yeah, so it means that I make it a variable. I will call it x now. Okay, and then I am interested now in this area. That is more or less changing the symbols, but I want you to tell me what happens now. What can I write for this area? Can you help me to write it down? So this area is equal to what now? If I want to write it as an integral symbol. So what should I write? I should write the integral for my function. What is my function this time? It's f of t. D of t, because my variable is t, not x. But it goes from a to x. Yes, is that understandable? So I have done the same thing. I have just relabeled some of the variables to some new names, and I did the same thing. So is that understandable? That what I have written here is exactly this one. But the point is that what do you expect? If I start moving x around, I will affect this area. For example, if I increase it, I'm making the area bigger. If I make it closer to A, I am making the area smaller. So in principle, this quantity A, which is the area, depends on my choice on x. So what is, whenever this happens, you say A is what?
A function of x.
A function of x. And then instead of writing it as A, you just write it as A of x to show this dependence. Yes. So in this case, even though I can call it still A, but it would be better if I call it A of x. So by the way, that's a function. It's area, but it's a function. The question is that what is the derivative of this function? Yes. So the question is, what is the derivative of this function? Okay. So what we have done, we have introduced a function, and I want to calculate its derivative. It's hard to tackle the general problem immediately, but by the way, that's quite advanced. I don't know why they have put it in the book. So that's the more or less the right way to derive Newton's formula. Okay? But to understand, before answering this question in its full generality, let us just try to motivate ourselves with very simple examples. Okay, so let me consider some functions that we can calculate this area without the using of integral. For example, if I have a rectangle, if I have a triangle, I don't know, trapezoid, I can calculate the area without using the notion of integral. So let me just keep the simplest possible scenario for the time being. So I have this t-axis and I have this y-axis. Let me consider this function f of t, which is a constant function, by the way. For example, let me just take it f of t to be 3. And for example, I draw this, it becomes a horizontal line, which is this one. And as I told you before, let me leave the right-hand side moving, x. But let me, I don't know which number do you like, so let me choose this number to be 1, for example. X is some number larger than x, larger than 1, and I am interested in this area. But of course, this area is variable. It's changing depending on how big or how small x is. So I call this area A of x, but you can immediately calculate this area without actually the notion of integral, because that's a simple object, that's a rectangle. So tell me, what can I write for the area? So what is the area? The area is the width multiplied by the height, for example, in this case. So area is what?
X minus 1.
So it is x minus 1, which is, so from here to here is x, from here to here is 1. So what is left in this middle is x minus 1. Okay. And then you multiply it by what? The height, which is 3. And as you predicted yourself, a is a function of x now. Yes, so a of x is this one. Let me simplify that, so it becomes 3x minus 3. Yes? Now let us take the derivative. That's a very, very simple exercise. So what's the derivative of 3x minus 3?
3.
It's 3. Let me just draw your attention to one point here. Assume that I haven't started from 1. I have started from 2. The area will be different, yes? So for example, if I have started with 2, but it will not affect the derivative, you will see. So assume that I have started from 1.5, for example. Yes. And then I want to calculate the area again, so let me write it with this color. So this time, what should I write instead of this? I should write x minus what?
2.
X minus 1.5 multiplied by the height, which is still 3, and I multiplied it becomes 3x minus 4.5. And if I ask you what is the derivative, you will answer what? 3x. And this is interesting. This is the same function. So the derivative goes back to the function itself. So that is the point. Okay, so let me now choose another one that we can calculate. For example, let us focus on a triangle. For example, let me take this line this time. A line that passes through the origin. For example, let me write f of t equals to 2 times t. Okay, so what is 2 times t? If I put t, remember I have relabeled the x-axis to t-axis. So if I put t equals to 0, y value becomes 0 as well. So that is 1 point. For example, if I put t equals to 1, a y value becomes 2, yes? So that would be my line. So this is f of t. So let me write y equals to 2t, yes? And this point was 1. I don't know, might be, it is good to start from 0, go to up to some point to x, for example, here. That's too big, right here. I go up here. Now I am interested in finding the area of this right angle triangle, and I will call it a of x again. Okay, so how should I calculate this? I have to calculate this length multiplied by this height, but because this is a triangle, I have to divide by 2, yes? So what is the answer? From here to here is x. I multiplied by this height. Can you tell me what this height is?
2x?
2x, yes, because that's the function. It's 2x. So I multiplied by 2x. But I have to divide everything by 2 because that's the triangle. And then what do you get? You get x squared. And now I ask you to differentiate this. So it becomes 2x. And 2x is more or less the same function, but the label is t here, the label is x. So if I ask you what is a prime of x, you will answer this is f of x. Do you agree? Because if I ask you what is f of x, you replace t with x and you tell me 2x, and this is 2x. So the derivative of this f of a of x is f of x in this case. If I ask you what is this, you can also write this is equal to f of x. Why is that? Because in this case, if f of t is 3 and 3 is constant, it doesn't matter which input I put, everything, the output is always 3. So if I write 3, 3 is also f of x. So you see that the derivative of the area function is f of x in this particular case, independent of my choice of this number. And the derivative of this area function is also f of x for that function. And I think you can convince yourself that it doesn't matter if I start from another point. So if you don't mind, let us calculate this, by the way. For example, assume that I am interested in this area. I don't want to start from 0, I want to start from 1 this time. Of course, this is not a triangle, it's what is called a trapezoid, yes. We want to find the area of this trapezoid, so let me write with the orange color. So this time a of x is equal to, I don't know if you see the formula sheet, the area of a trapezoid is the sum of these two lengths multiplied by the height and divided by 2. I will use that one. So this height is how much? This number is 1. And the function is 2t.
2.
So this becomes 2. So I have to write 2, which is this length, plus this length, which I already know is 2x. I have to multiply it by what? This width, and that is x minus 1. And I divide it by 2. If you tell me how, I use the formula for the area of the trapezoid, and that is the formula. But let me simplify that. Before multiplying, I factor a 2 out. It becomes x plus 1, x minus 1. And then I have a 2 here, this 2 and that 2 are cancelled, and that's the conjugate rule, so it becomes x squared minus 1. And now if I ask you what is the derivative, you see you get a different area function. Your area function was x squared. Your area function is now x squared minus 1, but the derivative is what? 2x again. And that's exactly equal to f of x. Yes? And the point is that we want to show that this is not a coincidence at all. If you construct an area function in this form, one thing is clear. The derivative of this function is this function that you see here. Only thing that you have to do is to replace t with x. So that is the point that we want to come to it, okay? So the point is that this is motivated, of course, by this example, but by no means this is the rigorous mathematical proof. But the point is that if a function is defined in the form of an integral, we want to convince ourselves somehow. You cannot do it completely in full detail, rigorous, but more or less you can do it. So the derivative of this function that you see is just this function. The only thing that you need to do is replace t with that x. But that is what we want to show. We actually convinced ourselves in 2 cases, but we want to show that this is not coincidence. And that's always the case. Do you have any questions? Yes?
So you remove dt.
Yeah, dt is nothing.
The integral.
So, yeah, exactly. So there's a function involved. When you
Yeah.
have an integral, a function is always involved.
Yeah.
And a variable is involved. And now what I'm claiming is that using that function and that variable, if you set up an integral and interpret this as an area, but this area becomes something related to x by changing x, a will change, so it becomes a function of x, then I am allowed to ask what is the derivative of this function. We want to somehow convince ourselves that taking the derivative of this function is super simple. What you need to do is just take whatever you see here, replace t with x, that's your answer. Yes?
So derivatives and integrals cancel each other out.
Somehow, yes. Exactly. So you are integrating a function to get a new function, but now you are integrating this function, you are getting this function back. Yes? What is the question? You had a question?
Well, I'm just wondering what would happen if you did another variable than what's inside the f.
No, that becomes complicated.
Okay.
Yeah. So if you want to have different variables, so the important point is that I want you to understand this, by the way, this name of this variable is not important at all. That's just a label. Do you remember? I called it t. You can call it alpha. You can call it beta. And then you have, but the important thing is that what you have here appears here. So this becomes a function from the top limit, the upper limit, yes? Is that clear? And then they say that the integral, that the variable inside an integral is a dummy variable. Because if I change the name of t everywhere, not just one of them, everywhere if I change the name of t to another label, alpha, beta, whatever, I will not affect the result, yes? Because it means exactly the same area.
But shouldn't that be the case with all variables? Isn't that the definition? You could change, like, how a variable is represented, but it would still be the same thing. No?
No. For example, in the derivative, no, but let me tell you, so might be that's a little, I don't know why the book has chosen to talk, but this t, you need two variables, yes? You need a variable. So in principle, this number should be a constant when you have an integral. You start from a fixed point and you go up to a fixed point, and then you have a fixed area, you're supposed to calculate that. That is the meaning of an integral. But there is no problem if I fix the initial point and let the final point vary. Yes? So this is why I have chosen x. In principle, I could have used x here as well, but that is not completely right, because when I use x here, I mean the right-hand side, the right point. I am not allowed to use x here. So you have to differentiate between the variables, because if you put x here and there, people will see that this x is the same x as there. But I want to differentiate that they are not the same things. Yes? Okay, so let us see how it goes. So the question is that first of all, I want you to understand, this is of course a little bit a strange way, but it is a way of defining a function, yes? Is that clear? So I hope that you understand the quantity that I define here is something that is a quantity that depends on the choice of my x. If I change x, the whole value will be changed, yes? And that is easy by seeing this picture. If I start changing this x, so what happens? This area will change. That's clear. Okay, but then I want to talk about the derivative of a function. When I want to talk about derivative of functions, either I have already the rule for that function, for example, if it's a polynomial or if it's an exponential function, I know how to do that. But if this is the starting point, do you remember where should I start? If I have a function which I don't have it in my table and it still insists to find its derivative, there is only one way to do that. And what is that? If you have a function which you don't know anything about its derivative at the moment, and you want to find its derivative, there is only one way to do that. Yes?
The definition.
That's the definition of the derivative. There is nothing much I can do. Yes? So, I want to go back to the definition of the derivative. So, I want to see how many of you can give really respect to the soul of Newton and Leibniz to be able to write the formula for the derivative of area here. So there is a limit, I guide you. Yes? Yes?
F of x minus
Not
a.
f here, what is f?
Oh, a. Okay,
A.
then. A in brackets x minus h. And then plus a of x. And then at the bottom h, as h approaches to 0.
So how many of you agrees?
Yeah.
No?
You don't agree.
Isn't it supposed to be minus a of x?
Oh, yeah.
This should be minus.
Okay, mix them up.
Yeah, you mix them up, yes. So this is minus, this is plus. Yes? So that is the derivative of this function, whatever this function is. So this means that if I'm supposed to find the derivative of this function, I need to understand how can I calculate this quantity for small values of h. Yes? Okay, so this one I cannot prove it rigorously for you because you need a little bit more advanced theorems, but the idea becomes very clear. So now let us go back to our picture. This is the t-axis, and this is the y-axis, and this is my function f of t, for example. And then, so the point A is clear, and then I have somewhere here x. Yes? So if I tell you what is this area, you tell me it is A of x. Yes, this area. But now, what is a of x plus h? It means that would be the same area, but I move this line a little bit more to the right. X plus h. Is that right? That's the meaning of a. So when I say a of x, it means that I have the beginning point, say, at a, fixed, and the right point, I consider it x. Now I am asking you the same question for this quantity. You would say this refers to the same thing, but the right-hand side vertical line has moved to x plus h. Yes? So let me just draw it with a different color. So it means that I go h units to the right, and then I just draw this one. So I don't know how can I show it. So this black part that I am actually coloring here, this is the black a of x. And if I ask you how can you show me what is a of x plus h, can you tell me what is that? That is some area. Area from where to where?
From x plus h to a?
A. So it means that I would just hatch this area with a different color. Here. So the blue one, every blue one is a of x plus h. Yes? And now everyone agrees, if I subtract these two areas, what is that one? If I subtract these two blue ones minus the black ones.
X plus h minus x?
No, that is yes. But then in the picture, I mean.
It's only the blue part.
Only this, the one which is only colored with blue, yes? That part. So this one, let me just try to color it in this way. This one that you see, yes, this one that you see is a of x plus h minus a of x. Yes? Is it a rectangle or not?
No.
No. Because this is very close to be a rectangle. I have three straight lines. Unfortunately, this one is curved. So that is not a real rectangle. But the point is clear as before. Now I hope that you are experienced in that. This is of course not rectangle. But the deviation of this shape from being a rectangle becomes negligible if h becomes a smaller and a smaller. Is that clear? So this is why I would say that if I ask you, can you give me an approximate value for this? Can you tell me or not? If I ask you, of course my point is to find the exact value here, but because h is going to 0, I can convince myself that this is approximately something. Can you tell me what that thing is?
Is it a of x?
No. No, you see that this is not negligible that much. So you are ignoring completely the area.
Yeah.
And that's one way. Yes, but if you want to do better, so you need to approximate this area with a rectangle. At least, instead of throwing everything away, you just throw this part away. Yes, what you did, you threw everything away, yes? Yeah. Okay, so if I want to consider this one, so what is this width?
X plus h minus x.
Which is?
H.
H, yes? Multiplied by this height. What is this height?
F of x.
F of x. Agree or not? So this one is the orange part. Of course, you see that this is more or less negligible if I want to approximate it with this rectangle, and it becomes better and better really if I make this h smaller and smaller. The area that I am making is very small. And that is valid because I am interested when h goes to 0. Okay, now remember you want this fraction, so I have to divide everything by h to get an approximate value here. So a of x plus h minus a of x divided by h is approximately f of x. And then when I take the limit, in the limit it becomes equality. don't forget about the intuitive notion of the limit. Of course, understanding limit from rigorous mathematical point of view is rather technical, but understanding it is not hard. So this means that I know that this quantity is approximately the value of f at x. This approximation gets better and better when I am making h smaller and smaller. So in the limit scenario case, the limit becomes exactly equal to f of x. And that's what the proof, yes. So a prime of x, which is this limit, is equal to f of x. So that's a very nice relation. So this area function, its derivative of the area function is f of x. So I want you to write it again. So if I have a of x, which is equal to integral from a to x, f of some variable, some label, then you realize that a prime of x is just the function that you see here. The only thing that you need to do is to replace the dummy variable there with this upper limit. Yes?
Does this only work when we already have an integrated function? Like, let's say we have only the derivative and we want to find the area of it.
Yeah, that's a different story. So then you have to calculate the integral of the derivative, of course.
Okay. So it
Because
only
if
works.
you have the derivative function, so if you want to find the area below, if this is the derivative of a function, and you want to find the area here, and then of course you have to calculate this from a to b.
So
Then it becomes f of b, as we will see now, f of b minus f of a.
So they only cancel. So it only cancels when you're deriving a already integrated
It cancels
function.
in both directions. So
Okay.
here I integrated first,
Yeah.
and then differentiated.
Yeah.
So you see, I integrate first, and then I differentiate it. It becomes f.
Yeah.
This is more or less the other way around as well. So if you integrate first, and then, differentiate first and then integrate, it does not become exactly f of x. It becomes f of x minus f of a. So you will get something extra, a constant extra there.
Okay.
Yeah, but more or less it is cancelling the derivative.
Okay.
Up to an additive constant. Okay, so this is what I want you to understand. Is that clear now? So more or less, this is, by the way, if you go to more advanced texts, this is more or less the proof. The only thing that you want to make it rigorous is understanding this really from, you need one more theorem to really understand this rigorously. Okay. Okay, let me ask you one question. So can you tell me what is a? Because that's a function, I am allowed to calculate it at different values. So f of, what is a of a? And you answer this question. This is your function. I am asking you, tell me what is the value of the area function at the particular point a. Yes?
F of a?
No?
Oh.
Be careful, just imagine what is the meaning of area function. So area function measures the area below the curve of f of t starting from a up to x. But I am making x the same as a. So what will happen?
0.
It becomes 0 because two lines are the same lines and there are no areas left, yes? So you see, if I ask you, if x becomes 1, what will happen to this orange area? If x becomes 1. When I am making x closer and closer, I am making the orange area smaller and smaller. But if I exactly stand on 1, there are no areas left, yes? So the area will be 0. So a of a is 0. Yes? And that is very nice formula. Remember, if you have an integral so that the lower limit is equal to its upper limit, you really don't need to calculate it at all. It is 0. Yes, and by the way, that is also I unfortunately erased that. I don't know why. So do you remember this formula that I mentioned? Integral from a to b f of t d of t. What is this? This is the limit of sigma f of ti delta t. I goes from 1 to n goes to infinity. And if I tell you what is delta t, you tell me that delta t is b minus a over n. Yes? Now, if a and b are the same numbers, delta t is what? 0. And if you put delta t 0 and you multiply by any number, it becomes 0. So you will get a bunch of zeros and then everything is 0. So this integral becomes 0. Yes.
When you say d of t, well, dt,
Yes.
is that derivative? Or is that delta?
No, I told you before, this dt is the small version of delta t.
Okay,
The
yeah.
delta t is the length of each one of those subintervals. The way that you can think about d of t is the small version of this delta t. Yes, that's the way that you can think about it. Okay, so that's one thing. Okay, so is that clear? So this is something when we proved, and I ask you what is a of a, you answered me that a of a is also equal to 0. Okay, now tell me what is a of b? Can you tell me what is a of b? A of b means go to your function, replace x with that value b. So it will give you integral from a to b f of t dt. Yes. Okay, now let me clean this. Okay, now let me ask you, let capital F be a primitive function for little f. Do you remember? Let me just ask you. What is the meaning of capital F be a primitive function for little f? What does it mean? Yes? Hussein? Yes?
Doesn't it mean that f is the derivative of f?
Yeah, capital F derivative is f. That's the mean. Okay. So, the derivative of capital F is little f. We also learned that the derivative of a of x is also f of x. Yes? So you see, if you tell me what is capital F, I don't know, but I'm telling you that assume that f is a primitive function for little f. It means capital F derivative is little f. On the other hand, the area function's derivative is also little f. So this means that a prime of x and that f prime of x are the same. Yes? And then I want you to answer this. Of course, if you remember, I told you that what I want to write here is true, but you cannot prove it because it needs more advanced theorems in mathematics. But I hope that you remember, if the derivative of two functions are equal, if two functions, so you see that f is a primitive function of little f. Capital F is also a primitive function for little f, because the derivative of these two functions is the same function. So can you tell me how they are related? That was important. I told you that. You cannot prove it at the moment, but assume that, just have my words on it. If I have two primitive functions for the same function, what can I conclude about these two functions? Yes?
A of x is equal to the primitive of f of x.
No, better than that. I told you that. So do you remember? So you also did this before. So if I tell you that, what is the derivative? If you know the derivative of f is equal to f, if you add any constant to this function and take the derivative once more, it becomes the same function again. This you know.
Yeah.
This is easy to prove even at the high school level. But the hard one was the converse statement. The converse statement was, if I have two functions to be the primitive function for the same function, what can I say about two functions? You see, assume that I have one function, capital F, differentiation will give me f, capital G, differentiation will give me f as well. I have two functions whose derivatives are the same function. What can I conclude about these two functions?
They're
Yes?
equal. They're equal.
No. And then I told you that, for example, x plus 1, x2 plus 1, the derivative of this one is what? 2x.
Yeah.
x2 plus 5, the derivative of this one is also 2x. But are these equal? No, can you correct it yourself?
So could it be that the primitive function is the same? Because you just
No,
have plus equal.
that's the meaning. It's a primitive function. X squared 1 is a primitive function for 2x. Why? Because its derivative is 2x. X squared plus 5 is also a primitive function for 2x because its derivative is 2x and they are not equal.
Yeah. But if we take the primitive function of 2x...
There is no the primitive function here.
Yeah, but it will become x squared. It will become x squared and then plus c.
Yeah? X squared divided, yes. Then what?
I don't know.
No, the point is that what can you say about these two? I told you, if you remember, by these two. Do you want to say something?
They only differ by a constant.
An additive constant. And that is not trivial at all. Because you might say that, okay, I see this function, its derivative is 2x. But might be, there is a very complicated function so that you differentiate it and for some strange reason, some cancelling things happen, and at the end I will get 2x. Because when you have a complicated function, when you differentiate, you have to use a lot of different rules, and they generate some terms. Might be by coincidence or whatever, these terms are somehow miraculously cancelled, and I end up with 2x. This theorem tells you that no, don't worry. If you find one primitive function for your function, every other primitive function is that function plus or minus a constant number. Not they don't differ that much. But this is not, we can prove it right now, but you need to understand it at least. One statement is very trivial. If I give you a function, if I give you a primitive function and I add a constant to it, definitely it becomes a new primitive function. That is very simple to see. But the point is that if I give you two primitive functions for the same function, is it guaranteed that they are the same or just differ by an additive constant? The answer to this is yes, but this is not trivial. I want you to understand the problem. Is the problem understood? Yes? But now, this is extremely important, by the way. This is why you always find one primitive function and add a c to it. By the way, think about it. Why we just add a c to it? Because if I find a primitive function and there are different primitive functions for the same function, I have to write all of them. When I say write all primitive functions, do you remember all primitive functions, the primitive function, a primitive function? So when I ask you to write all primitive functions, what do you really do? Do you look for all of them?
No.
In principle, yes, but you just find one of them and add a c to it. The reason is that this is guaranteed to cover all of them. This is important, but not trivial, by the way. Okay, now I want to go back here. This function and that function are the primitive functions to the same function. Okay, so let us just forget about this. So this means that these capital F and capital A are primitive functions for the same function. So what can I conclude from here? So what can I conclude? I can conclude that A of x is equal to, so let me write, f of x is equal to what? A of x plus a constant. Is that understandable? So this is that I proved today for you. This is, I am assuming myself, I am assuming that f is a primitive function. Now I realize that these are primitive functions for the same function. So it means that one of them, whichever you want, is the other one plus a constant, not that much difference. Only at most an additive constant. Yes or no?
Yes.
Okay. And now the point is that unfortunately I don't know what that constant is. And I want to understand the constant. Okay. I change this x to a everywhere. Yes? Now, what is a of a? Do you remember? It's on the board.
0.
It's 0. So this means that f of a is c. But do I know c? No. Because still I don't know f of a. But I know that c is that f of a. Then what I do, I go here and put it back into this equation. So this becomes f of x minus is equal to a of x plus f of a. Yes? Agree or not? Then I move this f of a to the other side, so it becomes f of x minus f of a is equal to f of a of x. Now I replace x this time with b. Yes? So then I would say that f of b minus f of a is equal to a of b. Yes?
What was the question?
Nothing. I'm exploring something. Yes? The question is nothing. You need to follow the calculations. Yes?
Yeah.
The whole point of looking at a movie is that you don't know what happens at the end. Because if you know what happens at the end, it's not interesting. So then we will wait for... So you need to follow more calculations. Are they hard? The reason that becomes a little bit convoluted is because your memory was a little bit blank here. Then I have to explain there. But the things that I was doing was so straightforward. Let me just review. We introduced the function today in this form, and we proved that the derivative of that function is f of x. Another way to this is that capital A is a primitive function for f. Yes? And now I am telling you that assume that f is a primitive function for little f again. So it means that f prime of x is f of x, a prime of x is f of x. I got two primitive functions for the same function. According to my explanations, one of them is an additive constant plus the other one. Yes? And then I replace x with a. You might say, why we are doing this? You need to be patient a little bit. Instead of x, I put a, but I knew that a of a is 0, so I replaced a of a with 0, and I got f of a c, and I put it back here. So then it becomes f of x equals to a of x plus f of a, and then I move this one back here, then I replace x with b this time. So what happens? I get this. Yes? So a of b is f of b minus f of a, and then we are at the end more or less. So f of b minus f of a is equal to, what is a of b? A of b is on the board. Yes? So it is integral from a to b f of t dt. And that is Newton's formula. Yes?
Oh.
So Newton's formula tells you that. Is your goal to calculate this integral? We will say yes. Newton's gives you a method. Newton's only asks you to find a primitive function. Whenever you have that primitive function, put this number in that primitive function, put this number in the primitive function, and subtract them. It becomes the answer. Yes? So I would write Newton's formula here. Integral from a to b, f of t dt is equal to capital F b minus capital F a. Yes? And if someone asks you, what is this capital F? You would say that this capital F is what? Is a primitive function for little f. Yes? And this is the reason that in the first part of this chapter we studied how to find primitive functions. And I told you that at that point finding primitive functions was just a mathematical curiosity. I give you a function, you differentiate, now I give you the this new function and I ask you, could you guess what was the original function? But now, why this is important? Because you are able to calculate integrals using primitive functions. And hopefully I was able to convince you that the notion of an integral is important. I gave you two examples, one from geometry and area finding, and the other one for finding the distance of a particle moving with a varying velocity. Yes? So this is the way, this is the Newton's formula. And now that we don't need label t, you see that t doesn't appear on the right hand side, so it doesn't matter which name, but what is the common name we usually use? In physics, t is a good name because it represents time, but in mathematics usually we use the variable x. So this is why in books you do not see it with t, you see it with x. And this is extremely important formula. By the way, you can totally forget about what I told you today. It doesn't affect, but because what you need to know in the exam is how to use the formula. This is the somehow derivation of the formula. Yes? And that is extremely important, by the way. What is the enjoyment of just memorizing something and use it? But now you understand that it's a very nice journey, actually. So this was very interesting to see that this area function is somehow related to derivative. Yes? Now, so the derivative didn't come into the game directly, but if you are smart enough to define a function in a very strange way, it turns out the derivative of that function is your original function. So it means that you are artifacting a very particular primitive function for your function. Yes? And using that you can understand. Okay. Now, I just want to give you simple examples and then we end up this lesson. And the good news is that I don't know which one we have to follow because I don't know, national exam comes based on this book or based on Origo book. They are not exactly following the same syllabus. That is very strange because, for example, I think in Origo book you also have calculating volumes in Math 3C, which I really don't like because they will touch a little bit of it. But this book has talked about areas in full detail and then leave everything for volumes in Math 4. So I think that would be a little bit reasonable. I don't know. So I will follow the book because the next actually this chapter is finished. Because the next section we want to learn how to use Geogebra to calculate primitive functions and integrals, which is also very good. Okay? And I know that in the national exam, in the part that you're allowed to use the calculator, you get integrals that you cannot calculate analytically and you have to use your calculator. And the bad news is that do you know how to calculate integrals using your calculators? So you also need to learn that. Yes? Okay. So let me just, before ending this lesson today, let me try to solve some problems using this. By the way, there is another symbol for that, so let me write this in this form. Integral from a to b, f of x dx is equal to f of b minus f of a. Sometimes you see people write it in this form. Okay? And that is the meaning of this. So instead of writing f of b minus f of a, they write f of x. Be careful, this is not integral sign. This is just a vertical line here. And then you write a little bit lower and b a little bit above. And this means this symbol, whenever you see this symbol, it means f of b minus f of a. Yes, that's just a symbol. There's nothing into it. Okay? So for example, if I ask you to calculate integral from -1 to 2 f of x squared dx, you want to calculate this integral. If you want to calculate this integral, you need to ask yourself about a primitive function of the function sitting in the integral. And the name of that function is integrand, if you remember. So you need to ask yourself, can I find a primitive function for my integrand? And that is the topic that we already studied. So what is a primitive function? You don't need to find all of them. So there is no point of putting c there. So a primitive function for this, what is that? Yes?
X to the power of 3 divided by 3.
Yes. So the formula, do you remember? You have it in formula sheet. So it was x to the power of a was 1 over a plus 1, x to power a plus a constant is not needed because what we need is just a primitive function. So I can consider c to be 0. And then it means that it becomes 1, 3, x to the power of 3. Yes? And then I draw this vertical line in front. This is very handy, by the way. And then I put -1 and 2 here. It's extremely important when the process of finding a primitive function is finalized, you are no longer allowed to keep integral sign. Yes? You have to draw this vertical line in front. And the problem is not finished because this means what? My recommendation is really to separate into two problems. Replace x everywhere with the upper limit and calculate it until the very end. So this becomes 8 over 3. And then do the same thing with the lower limit. So it becomes 1/3 minus 1 to power 3 and calculate it. It becomes -1 over 3. And go back to horizontal line by writing the number above minus, you see this minus sign is coming from the formula, minus the number that you got below, which in this case includes another minus sign. So what's the answer there? It's 8 over 3 plus 1/3, and the answer becomes 3, because 9 over 3 is 3. By the way, if someone asks you, should I write a unit in front of it? No. Remember, integral is a pure number. But if you are using the integral for calculating the area, then of course at the end you have to write 3 area units. But here I'm just asking you calculate this integral. Yes?
What if you were to have an upper limit of infinity?
No, that is called an improper integral, and then you will study it in the university. Yes.
But also,
Yes.
which is the problem for integral?
I don't know. You need to see which on the Casio calculator is probably better.
What
Yes,
if you
you
don't
need
have
to
it?
understand it yourself. But let me, by the way, try to see how it goes in Geogebra, and then we can continue later, okay? Okay, so if you go to Geogebra, if you want to do these calculations, of course you can do this in the algebra view, but it will always give you approximate values. So it is extremely important to go to CAS view if you want to do these sorts of calculations, yes?
Okay.
And then Geogebra is also capable of, by the way, you see the integral sign here.
Are you
You also
recording?
see the derivative sign here, by the way. So let us see, but I prefer to type rather than picking up
But
these
are you
signs.
recording?
Yes, yes. Thank you for reminding. That's always good to remind. Thank you. So what I am doing is actually right integral, I think. Yes. Oops. Integral. So you see that's function. I think integral, by the way, integral here means primitive function. Because you see, integral syntax only gets you a function. And if I just give a function without the lower limit and upper limit, it cannot be the integral that we have in this sense. So this integral means definitely my impression is that that is a primitive function. So let us check. So for example, if I give x to the power of 2 here, so what was the impression? It will give you what?
2x. No.
No?
1 over 3
X to the
times
power of
x3.
3 probably plus a constant. Yes. So 1 over 3 times x to the power 3 plus a constant, but GeoGebra has used C1 because probably if you have different constants, it will change this index. Yes?
Yeah.
So remember, just integral and then the function gives you all primitive functions, not only one of them. That's so for example, you can see more complicated functions. I don't know if GeoGebra is capable of doing those. So I don't know. You can write exponential function, for example. No, exponential function. How it starts with literally. No.
Maybe a to power x.
No, it should be some. It's here. So e is this one to the power of, for example. By the way, you should be able to tell me this one as well. So we don't need this one. Okay, so 3x. So what is a primitive function for e to power 3x? Do you remember? No, you should remember these things.
It's not 3x.
I don't know why it disappears. It is 1/3 e to the power of 3x plus c2. Of course, you should call it c1.
Yeah.
But GeoGebra, because needs to keep track of different things if you want to do something. So remember, this integral is just this one. But this calculate that the one that we calculated here, you need to type integral. But so you might have different variables. That's also interesting. Then you choose function and variable. For example, let me just test your understanding. I give you the function here, xt. Okay? And I take my variable to be x as usual. Can you tell me what is the answer?
No.
Thank you very much for disappointing me so frankly.
You're welcome.
Thank you. Okay. But anyway, try a little bit harder.
When you say xt,
So I have two variables, x and t. I multiply them. Do you
Okay,
remember,
okay.
you always ask me what is the role of dx there?
Yeah.
One role is, of course, I told you, this is the infinitesimal version of delta x. But that's also another reason that we write it, because it tells you which one is the variable if you have more than one variable here.
Yeah.
So here, when I write, but of course in GeoGebra you do not see dx. You can just tell the GeoGebra which one is my variable. So I am telling GeoGebra, find a primitive function for x times t, but I am telling GeoGebra that x is the variable, not t. So it means t is a constant, like 5, like 10. So let me ask you, what is a primitive function for 5x?
give me a second.
What is a primitive function for x?
Give me
By
a
the way,
second.
you are being published on YouTube. Yes?
A primitive function for x.
Yes?
1/2 times x to the power 2.
2. A primitive function for 5x.
1/5 times x to the
No,
power
no. Primitive function for 5x. If you remember, I told you that if you have a multiplicative constant, don't do anything with that multiplicative constant. Just find a primitive function for x again. It becomes 1 over 2x squared, then multiplied by 5.
So
So
5
it
over
becomes
2x
5.
squared.
So instead of doing that, let me just do this one first. I ask you this, yes? In this case, I don't need to specify x is my variable, because there are no more than one variable. It doesn't hurt, of course, but why should I? That is a primitive function for 5x, because you take 5 away, and you ask yourself what's a primitive function for x, the answer is 1 over 2x squared, and then you multiply it by 5, it becomes 5 over 2x squared. Now let me go back to the same question that I started. Integral of this function with variable. This time I write x times t, and I tell the variable is x. I'm telling GeoGebra the variable is x. Can you tell me what the answer is?
Is it t over 2x squared?
Yes. T over 2 times x squared. Because t is playing the role of 5 here.
Yeah.
So and then let us see. Oops. Because probably, I don't know why this is the case. Probably GeoGebra doesn't understand this.
Maybe put tx instead?
Yeah, might be. I should write a dot somewhere. So let me just put the dot, see what happens now.
No, that's decimal.
Are you sure? Yes. So
Pretty
what
sure.
is? Oh, okay. I need to use the cross. Yes.
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 But that's very strange if GeoGebra doesn't understand this. Yeah, it understood. Yes.
Okay.
1 over t, 1 over 2 x squared. So we have to be careful. We have to use the cross for this. Now, can you tell me what will happen in the other way around? So if I write integral with the with this one, but this I would write x times t as before.
Yes.
But now I tell GeoGebra no. For some reason, t is my variable. Yes. So what is your guess for the answer?
Is it x over 2 t squared plus e?
Yes, x over 2 t squared plus e. That's correct. So this is the reason. Sometimes you have more than one variable. You have to specify which variable is the integration variable. And in the handwriting way, dt, dx will tell you which one is the variable. So if I have, in the exam, you see xt dx, it means x is variable. If you see xt dt, it means t is variable. Yes? And then we also can calculate integral. You see integral, a function, a start value, end value. This is exactly what we did today.
Yeah.
So I choose this one, and then for example, what was the function here? X to the power of 2. What was the starting value? -1, if I remember correctly. And the final value was
2.
2. And we got 3.
3.
Yes.
Yeah.
And the answer is 3. So that is the way that it works. So you see that Newton's theorem actually reduced the problem of calculating integrals to finding primitive functions. But finding primitive functions, unfortunately, sometimes is quite hard and sometimes is impossible. We have to artifact new functions whose primitive functions are the functions that we are interested in. But at least you understand how to use GeoGebra to calculate these. But I will, of course, stop the lesson today right here, but later we will practice a little bit more with these integrals and areas and everything. But I would recommend, so I mean that the lesson is finished. I don't see any other thing we have to do, so I will update the Google Classroom and I give you a little bit of time.
And the test is tomorrow.
Yeah, the test is Wednesday, yes.
Okay.
Yes. Yeah. But I think sooner or later we have to have this test for integral part as well, okay?
We could just skip it.
Let's combine with the other.
Really, who
No,
likes
the other one is probably long. I don't know, that's up to you. That's better for me if you want to combine exams.
Combine geometry with integrals.
Weren't you talking about the way that we were going to have like a final test for the last chapter?
Yeah, just let me close this and I will come to you. Thank you.